At this point, we have pretty much all the information we need, both from an instrumental and mathematical point of view, to understand many X-ray diffraction measurements. And in the next few segments, we're going to be talking about some specific applications of this where specialized techniques are required. The first of these is going to be protein crystallography. I should give the caveat that I myself am not a protein crystallographer. However, the basic idea here is pretty straightforward and well understood. First, some reviews. I'll remind you when we talked about the crystal lattice and the crystal reciprocal lattice. So we say that we have in a crystal repeating units defined by these vectors R, M, N, O, where these are integers. And we said that in order to get non-zero diffraction, this momentum transfer Q had to be at a reciprocal lattice vector, and the reciprocal lattice was actually defined in terms of the real lattice. So if you know the real lattice, you know the reciprocal lattice, and vice versa. Furthermore, the intensity depends on several things. There's this lattice sum, which is non-zero only if Q is at a reciprocal lattice point. There is a sum over points in the basis, the atoms that go into the unit cell, and then there is the form factor for each individual atom, which is in general tabulated. So the program for crystallography is discussed in an early segment, assuming that we have a single crystal, not a powder. For a given wavelength, we have some orientation of the incoming beam. We determine all the possible orientations of which the crystal will diffract, and the orientations together with the directions of the outgoing beams tell you about the crystal symmetry, whether it's cubic or hexagonal or trigonal or whatever it might be. Those angles, the two theta values, tell you what the plane spacings are, and so between those two things you can figure out what the unit cell is, and then the actual relative intensities tell you how the atoms are actually arranged in each unit cell. So protein crystallography is one of the most challenging implementations of this. In modern molecular biology, you have a given protein or enzyme or whatever, you want to understand not only what it does, but how that is related to how it's constructed, how it's put together, where the atoms are, where loops and so forth are. These are very large, complicated molecules, and so it's a challenging problem to determine where the atoms are. If they are ordered in a regular lattice, however, we can use crystallography to determine atomic positions. It actually requires a substantial amount of computation, and modern protein crystallography didn't really develop until the advent of easily accessible large-scale computing. You should notice, however, that even if you have completely solved a protein in a crystal structure that's in a crystal in a biological environment, it's probably swimming around in an aqueous solution or perhaps attached to a membrane or something, and it may actually be packed quite differently. Nevertheless, you can still use the results of crystallography to inform your ideas of what it might be doing in that more important environment. The first step in protein crystallography is to grow a nice single crystal, and that is actually quite difficult. It's an art in itself. You want to make sure that you don't denature the protein in the process, change its chemical structure. These things are very small, probably a millimeter or less across, and they're typically very delicate, hard to handle. The next step is to perform an X-ray diffraction measurement, or more precisely a whole series of measurements. So you typically have something like tens of thousands of individual reflections. In this picture here, each one of these dots is an individual Bragg peak. The way pictures like this are obtained, if you just put the sample in the beam in some orientation, you only get a few spots. But if you rotate it about two angles, a very small amount, what's known as a precession or oscillation photograph, then peaks that are close to the diffraction condition get brought sort of into focus. And so then you get an image like this that represents one plane in Q space. The next step, obviously, is to analyze that. So as we said, the peak positions, when put together, unambiguously give you your lattice parameters. And you can see here, these aren't arranged on exact lattice. There's places where there are missing peaks. The patterns of missing intensities actually give you important information that tell you something about the space group, and that in turn provides some important constraints on the possible positions of atoms within the unit cell. And now, to continue from that, you have to use pretty extensive computation. I should say that this is, at this point, pretty much of a solved problem, and they have very sophisticated packages that do this work for you. You combine what you know, chemical knowledge from what you know about the protein, and various constraints to simplify the job as much as possible. In the last segment, I also mentioned the phase problem, that we measure intensities rather than amplitudes. A method of solving this that I didn't mention is that if you have n atoms, in principle you have 3n positions that you need to determine, 3n unknowns. If you have more than 3n reflections, then the problem is overdetermined, and that can actually help to solve the phase problem. As I discussed before, the word resolution gets used in two rather different ways. The better your angular resolution is, the smaller the width of these things, the better you can measure the sharpness and shape of individual peaks and learn about things like defects in crystallite size. For protein crystallography, that typically isn't so interesting. You don't usually really care that much about that. What you do care about is spatial resolution. The higher the Q values, the farther you go out into theta, the more precisely you know atomic positions. That's referred to as spatial resolution. Very often they'll make an initial measurement not going very far out in angle. They'll call that a low resolution measurement, where you don't know where the atoms are all that well, and then that's subsequently refined. If you go out to larger and larger Q, you know the atoms to better and better precision. The last important step is visualizing what you have. Just a list of coordinates isn't very useful. So typically the last stage is you're viewing this in sort of a meta level. You're really interested in where the helices and sheets and so forth are, rather than individual atoms, and actually can be very helpful to look at this with some kind of stereo view to have a feeling for what the protein is actually doing. I can recommend here a couple of good web pages, and also a nice hardback if you want to go into really a lot more depth.